Andrea?
How does these letters stand for?
E for error. J, your performance measure what I'm trying to minimize.
Integral, square error.
No.
Oh, integral squared error, integral absolute error. Okay? Integral integrates error squared. Integrates absolute y of the error. The one I'm going to talk about now is integral, here I'll write it for you, time absolute error. And that minimizes time. 0 is the current time, okay? Start from current time to infinity, I want to minimize it. What's the idea behind it? The idea behind it is that it's okay to have error at the beginning. But I don't want error, high error to stay for long. By putting, this is a weighing factor. So essentially you put a weighing factor according to time elapsed. So you're okay with some error at very short times, but error should not stay long. Okay? The more an error persists, the higher the weight of it. Make sense? So, people did this performance measure with transfer function first order plus time delay, and did an extensive searching of the parameter space, the three parameters kc, tau I, and tau d, and managed to find relationships that summarize in approximate fashion the results of the optimization. Interestingly enough, I told you that IMC, the one that I told you, infernal control, is good for set point changes, but it's not good for disturbance changes. Yet the tuning we have for Ziegler-Nichols and Cohen-Kuhn is the same for both set point and disturbance changes. So these guys, and the reference you can find in the Seaborg, etc. textbook, these guys did the optimization for both disturbance changes and set point changes. And it became with different tuning parameters for the two. So when we look at that table, you see load and set point, type of input. Load means disturbance change. So if the primary job of your controller is normally the case, would be disturbance rejection, you use this tuning, and I'll explain how this works. If you have a case where your primary job is set point following, for example, you have a PCR machine that you want to follow a certain temperature profile, then you would use this type of tune. Clear? Now, you see here PI and PID. It's not the proportional with the PI and PID. And they have two parameters, P and I and PID, and they have for everyone two sets of numerical values. You can see here what they did. They correlated things as y equals the parameter A you see here times theta is the delay over tau. So they use theta for delay instead of d. So A, d over tau to the b, where b is this. And that y can be the product of k, kc, for proportional, for finding kc, tau over tau I for finding tau I, and tau d over tau, with one exception for set point changes. So what you usually have is KKC when I'm trying to find KC. That's the K of the first order plus time delay. In other words, that means Kc is going to be y over k. It's going to be tau over tau y. So tau y you would tune as tau over y, and y is tau d over tau. In other words, tau d is, that's the tau of the first order plus time delay, okay? Tau times y. Where in every case, y is given by the two parameters a and b. So a times d over tau to the b. So a quick example. Suppose you have Does anyone have your CSTR gain model? Anyone have your CSTR gain model? All right, okay, then I'll just do. I would have done the CSTR gain tuning. If someone has the CSTR gain model, you could give me right now. Nobody? All right. Okay, example. Tuning for disturbance rejection. With GC, let's say from GC equals minus 4 over 10s plus 1 e to the minus 3. Okay, so that means that k is minus 4, tau is 10, and d is 3. And let's say I want to do it, PI control. So, my Kc is 1 over k times y. In other words, 1 over k times a d over tau to the b. Okay, remember, and what is, so k is minus 4, d over tau is 3 over 10. What is a and b? A bit more space. So how do I find a and b? I'm looking for disturbances, load, and I'm looking for PI control. So, mode P is the Kc equation. When you say mode P, that means the equation for Kc. If they say mode I, the equation for tau I. If they say mode D, the equation for tau D. Clear? That is, Sean? You see here, it has the type of input, if I'm doing disturbance or set point, the PI or PID, so if I choose PI, have two parameters, Kc and tau I. So the P is for Kc, PI is for tau I. So for Kc, A is 0.859 and B is minus 0.977. Got it okay? So 0.859. So that would be 0.859 minus 0.977. Someone on the calculator can please calculate that. Notice Kc and K have the same sign. Okay? Okay, first order time delay, we're talking about our least stable system. And what will be between us? Well, oh, I thought you were calculating this.
No, no, I'm
Well, doing something you're not supposed to do in class. Can someone calculate this?
minus 0.696.
Two significant figures you can put on. All right. What about tau I? Tau I, remember the y is tau over tau I, so tau I is tau over y. So tau I is tau over a d over tau to the b. So tau was 10 over. Now it's different a and b. So for tau I look at this column. So a is 0.674 and b minus 0.68. Okay? So the tuning would be so 0.674 to the 3 over 10 over tau to the minus point. So what's that equal to? Is it a bit lower than 10? No. So, yeah, it is. Well, higher than 10.
6.55.
Oh, it's lower than 10? Okay. Yes. Oh, yeah, that's the negative part. 6 point what?
5.4.
All right. So you see how we did? Now, there is one exception. For set point changes, there is an asterisk. Note, this is always for disturbance set what we talked about. For set point changes, the relationship for y, for tau I, is different. For the others are the same, but for tau I, instead is tau over tau I equals a plus b d over tau. So we have a different relationship, a different correlation for tau I for set point changes. So just be aware, right? So here you have a second tuning method for first order plus time delay that you can use.
Would you say we have to watch out for
Hmm?
that? Would you say we have to watch out for something that's exceptional?
If you're doing tuning for set point changes, tau I has a different correlation between y, has a different expression for y. Y is this, except for tau I for set point changes. In which case y equals a plus b times d over tau. Correct. Yeah. Okay, clear? All right. So, some final closing things. And I'm happy that basically we, at this point, have covered everything that I absolutely wanted to cover. But one thing to mention is that all the controllers, and now probably you don't find them anymore. I think, oh, I do remember, an IPD team found an ancient controller they wanted to use for the project, and actually it was the very first controller they saw that had this. Instead of using KC, which you saw, even the Mo controller is not very new, is uses something called proportional band. Proportional band is defined as 100% over the absolute value of Kc. So it's something like an inverse of Kc. So in the old days, they would tune with proportional band instead of Kc. Be aware of it.
How long ago was that?
50 years? 60, maybe. I'm sure nothing in the last 40 years has used proportional band. All right. More important is a certain issue that we sometimes have with integral action and the cure of it. Integral action has action proportional to the integral of the error and has a tendency to drive that integral towards 0, which means that if you have accumulated a lot of error of one sign, it tends sooner or later to create some error of the opposite direction. This is called, this happens when a controller saturates. Saturates means it's at the bound, either fully shut or fully open for long periods of time. Okay, so you have the controller fully shut, long periods of time, or fully open, long periods of time. You'll accumulate, it stays fully shut or fully open because you have always maximum error in one or the other direction, positive or negative. So the integral accumulates and you get large integral of one sign. And that brings some undesirable action when finally it gets off the bound. So what is a common sense cure for this problem, which is called reset windup? Windup refers generally to integral action, so you can think like a coil of a spring being tightened. So what do you think might be a common sense cure for this?
Turn it on and off.
To avoid, say it?
Turn it on and off.
Okay. When your controller stays saturated a certain period of time, turn off integral action until it stops being saturated.
That's exactly what I meant.
I think so. So anyway, I took it that way. This is called anti-reset windup. So anti-reset windup is a feature on some controllers that turns off integral action when it saturates for long periods of time. Temporarily turns off integral action.
See you on Wednesday.
What is the most, I didn't talk about the simplest possible feedback controller. What's the simplest possible feedback controller, guys?
Open manual.
What do you think is the simplest possible feedback controller? Proportion is what I expect you to say as a result of this class. But even if you hadn't had this class, there's an even simpler feedback controller that we experience every day. I don't know, maybe some of you have a very fancy heating control system for your house, but if it's a fairly old house, at least like mine is, how is your heating or air conditioning working? Does it work, you set the dial at desired temperature? Does it work with PI or PID for the desired temperature? Maybe some new ones work that way, but the older ones did not work that way. How did the old ones work? Maybe they still work that way. No, that's how you get the measurement, but how does the controller respond? Does it gets the error, which is the difference between the dial that you have set and the measurement it takes on the temperature. But how does it work? Does it vary the speed of the heating? No, actually, even today it works over here. Does it vary the speed of the heating or the cooling? Does it control the fan speed or?
No, just on and off.
On off. Exactly. The simplest feedback controller is an on-off controller. That works. You set a band. So basically, you will have an optimal temperature, let's say 70